Hey everyone, welcome back. All right, today we are tackling what I consider one of the biggest, most important topics in precalculus, graphing rational functions. This is where a lot of stuff we've learned really starts to click. So let's just dive right in.
And I'm not kidding when I say this is like the ultimate boss battle of precalculus. Seriously, think about it. All the skills you've been grinding and leveling up, factoring, finding intercepts, getting the hang of asymptotes, they all come together for this one epic challenge. But hey, don't sweat it. No one goes into a boss battle without a strategy, and we've got a great one.
And this really gets to the heart of it. A rational graph isn't just some random squiggly line you're trying to draw. You should think of it more like a map that's defined by its fences and its landmarks. The fences? Those are your asymptotes. The landmarks? Those are your intercepts in any holes you might find. They literally tell you where the path of the graph can and can't go.
So here it is, your 6-step game plan. This is our strategy to win every single time.
And here's that roadmap, our 6-step strategy for graphing these things. Okay, step 1, and this is crucial, simplify first, always. Step 2 is to find any holes. We'll talk more about what those are. Then step 3, you find those vertical asymptotes, those electric fences. Step 4, you find your horizontal or slant asymptotes, which tell you what the graph does way out on the edges. 5, you nail down your intercepts, your key landmarks on the map. And finally, step 6, you just test a couple of points to make sure everything lines up. Follow these steps and you're golden.
Okay, enough talk. Let's put the plan into action with 3 levels of challenge.
Here we go, level 1, a pretty basic one to get us started. We're going to graph f of x equals 2x minus 4 all over x plus 1. So let's fire up that 6-step game plan and see what we can find. Okay, after running through our steps, here's the intel we gathered. Check it out. We've got a vertical asymptote, our fence, at x equals -1. We've got a horizontal asymptote, our guide rail, at y equals 2. And for our landmarks, we have an x-intercept at 2, 0, and a y-intercept way down at 0, -4. And believe it or not, with just those 4 key pieces of info, we can sketch this thing out almost perfectly.
All right, you ready for level 2? This one looks a little more intimidating, right? We've got g of x equals x squared minus 9 divided by x minus 3. So we got a quadratic on top, but this one has a little trick up its sleeve. There's a hidden simplification here. And bam! This is why step 1 is so incredibly important. You gotta simplify first. If you look at that numerator, x squared minus 9, that's a difference of squares. It factors into x minus 3 times x plus 3. And look at that. We have an x minus 3 on the top and an x minus 3 on the bottom. They cancel out. So this whole complicated-looking thing just simplifies down to the line y equals x plus 3. But that factor we canceled, it doesn't just disappear. It leaves something behind. That's right. It creates what we call a hole. So what is a hole? It's basically a single, tiny point where the original function is undefined, even though the simplified one is perfectly fine. It's caused by that factor we canceled out, because if you plugged that x value into the original function, you'd get 0 on the bottom, which is a big no-no. It's like a single missing pixel on an otherwise perfect screen. So how do we find the exact location of this hole? It's actually pretty easy. You just take the x value from the factor you canceled out. Since we canceled x minus 3, the forbidden x value is 3. Now, you plug that x equals 3 into your simplified equation, which was y equals x plus 3. So y equals 3 plus 3, which is 6. And there it is. The hole in our graph is at the exact point 3, 6.
Okay, deep breaths. Time for the advanced level, level 3. Now this one, h of x equals -2 over the quantity x minus 1 squared. This one makes a really cool, really unique shape. People sometimes call it a volcano graph or a waterfall graph, and you're about to see why.
So what's the big secret to this volcano shape? It's all about one little detail, that exponent. The fact that the denominator is squared, that little 2 is the key to everything. See, whenever you have a squared term like that in the denominator around your asymptote, it's a massive clue. It means both sides of the graph are going to behave the same way. They're either both going to shoot up to positive infinity, or they're both going to dive down to negative infinity.
Okay, so are they both going up or both going down? Well, let's do a super quick sign check. The top of our fraction is -2. That's always negative. The bottom is something squared, and anything squared is always positive. So what do you get when you divide a negative number by a positive number? You get a negative, always. This means the entire graph, the whole thing, has to be negative. It lives completely below the x-axis, so both branches have to plunge down together towards negative infinity. That's our waterfall.
Okay, so now that we've seen the plan work, let's talk about some common traps to avoid. These are the pro tips that'll help you get a flawless graph every single time.
This is rule number 1. It's fundamental. It is absolutely non-negotiable. You can never cross a vertical asymptote, ever. Think of it like a giant invisible electric fence. The graph can get really, really close to it, but it can never touch or cross it because the function literally doesn't exist there. It's forbidden territory. And here's the other big one, forgetting the whole. It's such an easy mistake to make. You do all that work to simplify the function, and you just get excited and graph the simple line. On the left, you see the graph of y equals x plus 3. It's a solid line. But that's wrong. The correct graph, on the right, is almost the same, but it has that one tiny, super important open circle at 3, 6. If you forget that whole, you're not graphing the original function anymore. You've drawn the wrong map.
So why are we doing all this? What's the reward for beating this particular boss battle? Well, this is where it gets really cool, because this math actually shows up in the real world. For example, take a look at this formula. This comes straight from physics. It calculates the total resistance in a certain kind of parallel circuit. Just look at the structure of that equation. It's one thing divided by another thing with a variable in it. It's a rational function. It's exactly the kind of thing we've been graphing.
And here is the payoff. In that real-world circuit, as you make that one resistor, R, bigger and bigger, infinitely large, the total resistance of the whole system gets closer and closer to, you guessed it, a horizontal asymptote. In this case, it's at y equals 10. So that line on the graph isn't just a math concept. It's a real physical limit. It means that with this setup, you can never get more than 10 ohms of total resistance. The asymptote tells you the absolute maximum possible. It's the boundary of reality for that circuit. And really, that's what I want to leave you with. These things, these asymptotes, they're not just lines we draw in math class. They represent real boundaries, real limits that exist all around us. So my final question for you is, what other real-world systems can you think of? Maybe in biology or economics or engineering. Systems that have these hard limits, these barriers that they can get closer and closer to, but just can never, ever cross. Think about it.